So you can start.
Okay. Welcome to the third and final live session of NPTEL course of thermal physics. So this week, for this live, we have not received any question from the uh, audience as such, or question from the students as such. So what we are going to do is we are going to answer few of the questions that was posted on forum, on several forums. So one such question in which I think it was asked, wait, just give me a second. Okay, I'll just open this question. Right. Okay, there is one question and there is second one. 5. Right. Okay, so there is one question from problem set 9, or rather problem set of like week 9. So the problem, let me plus start sharing the screen first, and then we just, yeah, share the screen. Yeah. So is the screen, computer screen visible?
Yes, it is visible.
Yes, sir.
Okay. So I'll do one thing. I'll just turn off the camera for now, because I'll be sharing the screen and all. Okay. So one question is from this particular problem number 9, and the question reads something like, in the derivation of QH and QC, why did not directly use the formula CpT2 minus T1 and CpT4 minus T3 like we did when we computed the heat exchange for engine cycles? Okay. To solve this, to answer this, the answer is very simple actually. See, this is a ideal gas Joule cycle in which we have two isobaric process connected by two adiabatic process. And of course, heat will enter the system during process 1 to 2 in this particular isobaric process, and heat will leave the system, leave the cycle from while going from 3 to 4 in this particular isobaric process. Now, because these are isobaric process, the temperature difference, we in order to calculate the heat, we have to use the specific heat at constant pressure. So we cannot use CV here. We have to use Cp times T2 minus T1 and Cp times T4 minus T3. Now that's exactly what we did in the solution. If we look at lecture 45, let me just open lecture 45, then we can understand it better. Right, in lecture 45, where we have, yeah, here we have solved this problem. Now, while solving, oops, sorry, we just took C, where is this? Is not working. Anyway, so we have used we have used QH is equal to Cp122 dt, and we have used QC. And then what we did was we actually took, see, here P1 and P2 is given and nothing else is given. So we have to express this temperature, express this integrand dt in terms of temperature only. So what we did, we took temperature as a function of pressure and volume, and because it's an isobaric process, this dp term will be equal to 0. So this term will be the only surviving term, and it is an ideal gas. So for an ideal gas, if we know that equations of state is PV equal to nRT, so we can use that to compute del T del V at constant pressure. We did exactly that, substituted it here, and we have got QH is equal to simply this V2 minus V1. Right. So similarly, we have used uh, QC is equal to V3. I mean, similar formula was used for QC, and we have got this Cp by Nr times P3, V3 minus V4. And eventually, this is the efficiency expression that we have got. Now, for the other question that was posted on forum, that was to do with lecture 54, where we were discussing thermodynamics near triple point. Now, somebody have rightly pointed out that actually there is a mistake in this three relations. This entropy is equal to latent heat divided for a phase transition. The change in specific entropy is actually latent heat divided by temperature, and I just made a mistake by writing the temperature in the denominator of the entropy, which will be actually multiplied. Temperature should be multiplied with entropy. So the correct relations would be, I'll just write the correct relation. Where is it? Wait. Yeah. So the correct relations will be latent heat of, what is it? Solid to liquid. Solid to liquid will be equal to S liquid minus S solid multiplied by TR. Similarly, S liquid to vapor will be S vapor minus S liquid TR, and latent heat of the last one was what? Vapor to solid. Vapor to solid will be S solid minus S vapor times TR. Yeah. But again, this will not change anything other than just, I mean, there is a mistake, of course, but it will not change this particular relation, because if we combine these three latent heat expressions, irrespective of whether TR is in the denominator or in the numerator, this internal entropy terms will cancel each other nicely, so it will be zero anyway. So the thermodynamics or the physics is not changing, but there is a mistake nonetheless. Okay. Now let us check the YouTube live link. Right. Yeah. So do we have any questions here in the chat? No, there is no question. Okay. So is there anything that we can discuss? I am just asking to the TS if there anything that we can discuss during this session. Okay. So if there is nothing specific, what I would like to discuss is the Gibbs phase rule. Just give a little more overview, a little more insight about Gibbs phase rule. Sorry. The Gibbs phase rule, the mathematical statement of Gibbs phase rule is F is equal to C minus P plus. Okay. Now okay. So what is C? C is number of components. P is number of phases. F is number of independent intrinsic variables. Also, this is called a degree of freedom. Same thing. So these are related by this phase rule. Now, the actual derivation of phase rule, which is a lot more mathematical, and we have not done that. We have just used a very basic, what you call argument-based derivation of this particular relation. Now, although we do not it does not look very complicated. It's a simple relation. But actually, I'm going to show you. We have already discussed this during these lectures, during the online lectures. But I'm just going to show you that this is actually a very powerful tool to discuss uh, phase transition and phase equilibrium. So let us take the example of a single component system. Let's say um, even more. Let us let us be even more specific. We just take water in a beaker. Just liquid water in a beaker. Now, in order to specify the thermodynamic state of this system, how many parameters do we need? This will be precisely the number of degree of freedom or F that is required from the phase rule. Now, in this case, C is equal to 1. And please remember, there is only one phase. So P is equal to 1, which actually gives F is equal to, what is this? C minus P plus 2. So it will be 1 minus 1 plus 2 is equal to 2. That means we need two parameters in order to specify or in order to give a complete description of this water in a beaker system if we consider that as a thermodynamic system. And please remember, the description does not change if we take an assembly of a gas assembly. I mean, now these two independent parameters could be any two of this pressure, volume, and temperature. Any two of this. We can take any two of this. Okay. So, and this is something that is well known, and we have been discussing this from the very beginning itself of the course, that if we know the equation of state, then out of this PV and T, only two remains independent, and because three are connected by equation of state, and just specifying two of these three parameters is sufficient to get a full thermodynamic description of the system. Now, this is first example. Now, let's take a second example, that water in equilibrium with steam. And this can happen, steam or vapor, whatever, water vapor. Huh? So in this case, C remains 1. It's a single component system, only water. Capital P. Capital P in this case will be equal to 2. And that immediately tells you F will be equal to 1 minus 2 plus 2 is equal to 1. That means, moment we have a phase equilibrium system between liquid water and its vapor, then the degree of freedom reduces from 2 to 1. Why it is so? Because now if we look at the phase diagram, please remember that liquid vapor is actually a first order phase transition. So this is defined by a phase line, right? So under this here it is liquid, above here it is liquid, and here it is steam or vapor. For water we call steam, but in general it is vapor. Now, if we specify any given pressure or temperature, the other point is already specified. Now we needed two parameters. Now it reduces to one, because we are talking about a phase equilibrium between water and steam that itself follows this Clapeyron equation, that dP dt is equal to L by T V2 minus V1, right? So because this equation, this line is a result, I mean, this is a solution of this particular equation, okay? Although sometimes we just cannot integrate it, but in reality, this line is actually a solution to this particular equation, which is so this equation actually defines the locus of this phase equilibrium point. So we need only one parameter to specify the liquid and better I would write just vapor, liquid vapor, and liquid vapor equilibrium. And I have taken the system as water in equilibrium with steam, and it could be any liquid in equilibrium with its vapor. Next, we take another example, that solution of salt, which is NaCl, simple NaCl, could be anything actually, salt, sugar, and instead of NaCl, we can also have KCl, does not matter, in water. So Just like in the first case where we have pure water in a beaker, now we add salt to it. What happens? Now component C becomes 2, phase becomes, sorry, capital P again. Phase becomes 1 because it's just liquid phase. So F eventually is 2 minus 1 plus 2, which is 3. Here it was 2, now it has gone up by 1, 3. Why? Because just think of it. If we want to define a thermodynamic state of a salt solution, how many parameters do we need? We need any two of pressure, volume, and temperature. And we need concentration either in per gram or per mole, whatever, but we need concentration nonetheless. Now, if we know any two of this pressure, volume, temperature, and we know the concentration of the salt, in principle, we can compute all other thermodynamic parameters, including free energies and all. Of course, yeah, free energies and entropy and everything from this parameters. So we need three independent degree of freedom. And please remember, these are very intuitive. I mean, when I solve this, it looks nothing new. But what I'm trying to tell you that whatever we have been discussing about phase transition or thermodynamic description of a system, this is all embedded in this simple looking formula that F is equal to C minus P plus 2. Huh? Okay, so just like equation of state initially looks like just a tool for solving problems or just giving a brief idea of a of the state of the system, but it turns out that equation of state contains all necessary information, including the information regarding energies, free energy function. Similarly, this Gibbs phase rule looks very simple, but it actually gives you a very good idea of the entire, I mean, how to get the entire thermodynamic description of this system. Okay. Now, 4. Now we have a saturated, another situation. Just I'm making it little more complicated. Saturated salt solution in equilibrium, sorry, in equilibrium with water, sorry, what not water, with solid salt. So we have a large amount of salt present so that the entire solution is saturated for that given pressure or given temperature. And there is a solid salt at the bottom of this beaker, in a beaker itself, in a beaker. Okay, so in a beaker, we have saturated salt solution in equilibrium with solid salt. Now what? Now component equal to 2 and phase also becomes 2. So F will be 2 minus 2 plus 2 is equal to again. So one of this could be any maybe pressure or temperature, and the other one could be other one has to be the concentration. So moment we talk about equilibrium between phases, please remember, moment we specify the, I mean, we say that we have a equilibrium between phases, we have this line in hand or this solution of this equation in hand. So that means one of these two parameters, which is temperature and pressure, or we can have a similar phase diagram in temperature in and concentration or pressure and concentration. If we want to, if we want, we can do that. So any one of this has to be specified and another parameter like, for example, concentration. So this entire description, thermodynamic description, or at least the number of independent parameters needed for the total thermodynamic description of the system is predicted very well by this Gibbs phase rule, even for a single component system and as well as for a two component or even higher more number of components. Even if we have more number of components, this particular rule will be generally valid. Okay, so that's all from my end. Is there any question from forum? No, I don't see there is no question. Okay, so if there is no question, it is already almost 20 minutes, and if no question have occurred, can we terminate the session?
Yes, sir.
Yeah. Okay, so let us do one thing. We'll just stop sharing. Stop stop sharing. Yeah, and fine. So we'll just we want to say thank you to all the students, and of course to the NPTEL team and the TS for your effort. And I hope everyone will be uh, doing good in the exam. All the best. Thank you.